The welding is the foundation of a steel fabrication, but even strongest weld can vulnerable to hidden enemy hydrogen, which could lead hydrogen-induced cracking. My name is Nadeem Akram and welcome to our educational video on hydrogen-induced cracking in welding. Today we'll explore the phenomenon of HIC, its impact on weld integrity and practical way to prevent it. What is hydrogen-induced cracking? The technical name of this type of cracking is hydrogen-induced cold cracking, but it is often referred to by other names that describe various characteristics of hydrogen cracks, such as delay cracking, cold cracking, heat affected zone cracking, or toe cracking. The hydrogen-induced cold cracking occurs in weldment due to the presence of hydrogen. It can manifest during the cooling phase after welding or even days later, possibly up to 72 hours. Hydrogen-induced cold cracking affects both the weldment and heat affected zones. Mostly these cracks originated in heat affected zones but may extend into the weldment. Four key factors can contribute to the formation of hydrogen cracks. Temperature below 300 degrees centigrade limit hydrogen diffusion and increase its embrittling effect. High hydrogen content weldment with high hydrogen level exceeding a threshold of 15 milliliter per 100 gram. Stresses greater than 0.5 of the yield stresses creates a driving force for cracking. Susceptible microstructure brittle martensite microstructure with high hardness exceeding 400 HV can less resistance to the crack initiation and propagation. It is important to note while heat affected zone cracking is more common, hydrogen crack can also occur within the weldment under specific conditions. Hydrogen can enter into the weldment through moistures from flux, hydrogen shielding gas from cellulosic electrodes, hydrogen within oil, grease, paint, moistures, and rust on the material surfaces. Hydrogen-induced cracking primarily occurs in coarse-grained region of heat-affected zone during welding. The intense heat of the welding arc breaks down the hydrogen-containing molecules into individual hydrogen atoms. These small atoms readily diffuse into both the molten as well as solid metal surrounding the weld metal. You might be wondering how hydrogen diffuses into the metal if there is no pores or cavities. The ferrous steel is primarily composed of iron around 97%, with a relatively large atomic size compared to hydrogen. Imagine iron atoms as basketballs and hydrogen atoms as marbles. This analogy highlights how hydrogen atoms can fit into the spaces between iron atoms. Another fact is that the solubility of hydrogen atoms increase at high temperature, allowing the hydrogen to diffuse into the metal. Let's take a look at a graph depicting hydrogen atomic solubility in relation to the temperature. In austenitic phase, there is a more hydrogen solubility than in ferrite phase. However, in ferrite phase as well as at ambient temperature, the mobility of hydrogen atoms increase in comparison to the high temperatures. This is due to the concentration gradient process, which is the movement of the particles through its solutions or the gas from an area with high numbers of the particles to the area with a lower number of the particles. This is quite similar how heat moves from the hot places to the cold places. Once welding is completed and metal solidifies, hydrogen atoms continue to diffuse outwards and escape into the atmosphere until the weldment cools. However, as the weldment cools down to the ambient temperature below 300 degrees centigrade, hydrogen diffusion slows down significantly. This leads to the trapping of hydrogen typically within the heat affected zone. Under specific conditions such as the susceptible microstructure with high hardness and a brittle nature along with high tensile stresses, these trapped hydrogen atoms can trigger hydrogen-induced cracking. Many studies are underway to understand hydrogen cracking. Based on my research and understanding, the welding hydrogen cracking phenomena are associated with three main behavior of trapped atomic hydrogen: hydrogen embrittlement, molecule formations, internal pressure buildup. Hydrogen embrittlement, this occurs due to the penetrations and diffusion of atomic hydrogen, which is believed to disturb the lattice bonding between different elements in steel. As a result, susceptible material lose strength, ductility, or fracture toughness. Molecule formation, dissociate hydrogen atoms can recombine to form molecule hydrogens or methane gas by reacting with carbon or carbides in the steel. These gases can accumulate in coarse grain or grain boundary regions, laminations, voids, or pore other favorable location within the steel. Internal pressure buildup. As a result of hydrogen molecule formation, the internal pressure can build up within the steel, contributing to the crack formation. If remaining two factors, susceptible microstructures and acting stresses, are also active. Presence and behavior of hydrogen is not the only factor which can contribute to the crack formation. The other two factors like susceptible microstructures and acting residual stresses also need to be activated. Absence of any of three can avoid the hydrogen cracking. What is a susceptible microstructure? Consider a light bulb or a bubble gum. If we could trap hydrogen gas inside a light bulb and increase the pressure beyond a certain level, the bulb would burst due to its rigid structure. Similarly, imagine forcing hydrogen gas into the bubble gum. The bubble gum will stretch and deform but would not burst because it is ductile. This analogy highlights the difference between the brittle and ductile material. The heat affected zone can become brittle due to the hydrogen, making it susceptible to the cracking under localized high stresses instead of undergoing plastic deformation, stretching like behavior. A susceptible microstructure is one that contains a relatively high portion of hard, brittle faces of steel, particularly martensite. The heat affected zone hardness is a good indicator of a susceptible, and when it exceeds a certain value. For carbon and carbon manganese steel, this hardness value is 300 HV and susceptible to the hydrogen cracking increase as hardness increase above this value. The maximum hardness of a heat affected zone is influenced by the chemical composition of steel, cooling rate of heat affected zone, and after each weld run is made. The rapid cooling is not the only contributing factor. The martensite structure cannot be produced unless the high carbon equivalent value is there. This is the only rapid cooling plus the high carbon value is the contributing factor for the martensite structure. Welding inherently introduces stresses into the joint due to the localized heating and cooling process. The severity of these stresses depends on several factors, including material thickness, heat input, joint design, component size and weight, joint fit up, the strains during welding, etc. Fortunately, there are several ways to minimize the risk of hydrogen-induced cracking. The cracking can be avoided through the control of following factors. Apply preheat to slow down the cooling rate and thus avoid the formation of susceptible microstructure. Maintain a specific interpass temperature, same effects as a preheat. The post-heat on completion of welding to reduce the hydrogen content by allowing the hydrogen to effuse from the weld area. Here one point to be noted, this is post-heating, which is done to diffuse out hydrogen from weld area. This is not a PWHT or post weld heat treatment, which is done to reduce the residual stresses. The next point here is to apply PWHT to reduce the residual stresses and eliminate susceptible microstructures. Reduce weld metal hydrogen by proper selection of welding process, consumable, etc. Use of TIG welding instead of SMAW welding. Use basic covered electrode instead of cellulose electrodes. Use multi instead of single run technique. Eliminate susceptible microstructure by means of self-tempering effect. Reduce the hydrogen content by allowing the hydrogen to fuse from the weld area. Use temper bead or hot pass technique, same effects as above. Use austenitic or nickel filler, avoid susceptible microstructure formation and allow hydrogen diffusion out of critical area. Use dry shielding gases, reduce hydrogen content. Clean rust from the joint, avoid hydrogen contamination from the moisture's presence in the rust. Reduce residual stresses. Blend the weld profiles, reduce stress concentrations at the toe of the weld. By understanding hydrogen-induced cracking and taking preventive measures, we can ensure the safety and reliability of welded structures. Remember, a little knowledge can go a long way in preventing a major disaster.